Oh man, I feel like a statistician. We've done one example of how to calculate power. Before I do more examples, I want to talk about some ideas that we could use. You don't need to know them, but they might help you understand why we made the choices we did. First off, we talked about how you could use S instead of sigma. That would involve us using t-scores instead of z. That would make things a little harder. Thanks to computers, it's not too bad, but it just complicates an idea that we don't need complicated.
I think you're overcomplicating it. What?
So we're just going to stick with z's to keep it simple. Also, we made sure it was one-sided. If you look at this picture, we had only one fence. We could have had a two-sided example, and there would be an extra fence. We would figure out where both fences landed, and then figure out where the probabilities were for each of those pieces. This second fence would be clear on the other side of the null, so far away from the red picture that there would be pretty much no power added to that side. So just to keep things simple, we're doing it only one-sided. Also, the alternative involves all the numbers less than 10. We've just picked one to keep it simple, but a computer could pick all the numbers. For example, here I'm going to tell the computer all the values we had, including 9 was our alternative value that we were using, and it's going to calculate all the values we just did, and the power, 0.912. There's some rounding error because the computer keeps track of like 18 decimals, so we had a little bit of rounding error there. But that's pretty much the same answer we got before, and now I can tell the computer, don't just have the value of 9, do every number. In fact, let's go not from 8 to 9. How about 8 all the way up to 10, which is where the null hypothesis was.
8, 9, 10.
And find the power values for all of those. What I'm going to have is not just a single value. I'm going to have a different power level for each of those. So, this is the power at 10 and at 9.99 and 9.98. And I can do a picture here. The example we used was a value of 9. And so the power level was 0.91, I guess 2 if you don't have some rounding error. But you could look at this picture and say, what if the alternative had used 8.5? Well, the power is going to be up a little bit, not a whole lot higher. What if I had used 9.6? Your power would drop a lot because you put the mu from the null and the mu from the alternative so close to each other. It looks like your power is going to be like about 0.36. This has a name. It's called the power curve. And it's very useful in real life to say, how far apart do the null and the alternative need to be for you to be able to detect things with high probability? Okay, that's useful. Sometimes people do this for sample size, like how much does your power drop if your sample size gets too low? Also useful. A little bit more work than what we're ready to practice in this class. So yes, we're going to give you a value for the alternative, ask you to calculate the power just for that, and then later in real life, if you need it, have the computer help you and make a curve for all the possible values.